The ionization energy is the amount of energy required to remove an electron from something. Here I have aluminum, and if I want to remove an electron to get an aluminum cation, I need to spend 580 kilojoules per mole of aluminum in order to get an aluminum cation. If I take this cation and I want to remove another electron from it, then I need to spend 1,815 kilojoules per mole to do this. This is called the ionization energy. This would be the first ionization energy. This would be the second ionization energy. If I wanted to get a +3 cation, then this would be the third ionization energy, and so on, the fourth ionization energy. If I look, I'll notice that there is an increasing ionization energy as I remove more and more electrons. And that is because if I have my positive nucleus and around it I have my electrons in their orbitals, as I remove electrons, the positive charge is going to remain the same, but there are going to be fewer electrons for that positive charge. As a result, the nucleus holds its remaining electrons more tightly because there is greater positive charge, so that should make intuitive sense. But that's not the only trend in ionization energy. If I look at the periodic table and I look at the ionization energy of the different elements and not of just the same element but taking off more and more electrons, I'm also going to notice trends going vertically and horizontally on the periodic table. So here I have the first ionization energies for a series of elements. On the left I have the ionization energies of the second row of elements. So this one right here. Choose a different color. So for this row, I have the majority of those elements' ionization energies. The green column is for this row right here. So I'm going to compare the ionization energies as I go across the periodic table, and then I'm going to compare the ionization energies of elements in different rows. So let's begin by going from the right side of the periodic table to the left. And I'm going to start with the right side of this second row, and I'm going to begin with neon. Neon is a noble gas. It has an octet, so it has the most stable electron configuration. If I want to remove an electron, its ionization energy is 2,088 kilojoules per mole. If I go to its left, fluorine has 1,681 kilojoules per mole. Oxygen, 1,314 kilojoules per mole. Nitrogen, 1,400. Carbon, 1,086. And if I go over to the left side, where I have beryllium and lithium, I've got 520 and 899. So if I look for a trend, I notice that they seem to decrease as I go from right to left, or if I look at it from an increasing perspective, the ionization energy increases from left to right. Lithium is its lowest, and then I increase generally from when I go from left to right. There is a notable exception here with nitrogen, but generally it's increasing. And if I think about why that is, I'll have to think back to my electron orbitals where I was filling in boxes like this. And I think about the valence electrons. I know that neon has the most stable configuration. Because it has the most stable configuration, it's difficult to remove electrons because the electrons are so stable. And lithium, on the other end, is one electron above a stable noble gas configuration of helium. So it is very easy for it to lose that electron, because if it loses that electron, then it gains a stable electron configuration. If I were to think of the goal of these elements being to get an octet, or 8 electrons in its valence shell, then this makes a lot more sense, this trend in ionization. The elements that would gain an octet by losing electrons have lower ionization energies than those that are close to gaining an octet by adding an electron. Fluorine, for example, has a high ionization energy because in order for it to gain an octet, it would have to lose many electrons, where if it were to gain one, it would only have to gain one. Same with oxygen, it also has a high ionization energy because it only needs to gain two, whereas if it wanted to gain a helium electron configuration, it would have to lose more. So that is what explains that. So now what I'm going to do is compare the elements but a row down. So here I have radon. I'm actually not sure what this element is. I've never seen it before. It's probably a very radioactive element that has a very short half-life. And I'm not sure what that one is called, but this one is polonium, this one is bismuth, this is lead, and I didn't include this one. I don't know why. I just didn't feel like writing it down. It's not important. This is barium, and this is cesium. If I go from right to left as I did before, I'm going to notice a trend, the same sort of trend. As I go from right to left, it decreases, or if I think of it from cesium to radon, it's increasing. Cesium has 382 kilojoules per mole, barium 503. It increases. Lead 813, bismuth 703. Oh no, that was polonium. Lead is 715, polonium is 813. And this element that I'm not sure what it's called is 926, and then radon is 1042. Same trend. Not as a large disparity between them, and one reason for that is going to be because these electrons are so far out in comparison with these ones from the nucleus that the effects are much less than as if they are closer to the nucleus. So there's a lot of electron shielding from those inner core electrons. But another thing to notice is to compare these two columns, the neon to the radon. These have lower ionization energies. Comparing neon to radon, it's almost half. Fluorine to this element, same thing, it's about half. Same here and here. The ionization energy is decreasing from top to bottom, or I can think of it as increasing from bottom to top. And again, it's because of the electron shielding. The nucleus is unable to hold on to those outer electrons as well as these ones, because these ones don't have as many inner electrons that are shielding its valence electrons. These electrons would only have the 1s shell that would be shielding a lot of these ones, whereas this one would have all of these 2s, 3s, 3p, 4p. It would have some d orbitals as well that are shielding it. So it has a lot of negative charge that is shielding these outer electrons from the nucleus. So its effects are reduced. It's easier to ionize these larger atoms. So in summary, the ionization energy is increasing on the periodic table. It's easier to think of it like this. It's increasing when it goes from the bottom to the top, and also the ionization is increasing from left to right. And it's also important to remember that for individual elements, the more electrons that I knock off of it, so the higher ionization energy I go from the first to the second to the third, those electrons are going to become more increasingly difficult to get rid of, no matter what element it is.